Hi, Lee with Ames Community College here with another learning moment. Today I want to talk about the derivation for the wind power potential equation. Here's the equation behind me, and let's go through it real quickly and then we'll see how we get to this equation. So we want to know how much power is available in a certain area swept out by those wind turbine blades. Presumably as we increase the area, we also increase the power that's available, and that it's determined by 1/2 times the density, this is a Greek letter rho, meaning the air density, times the cube of the velocity, the speed of the air. So those are the terms. Now that you've seen them, let's go through the derivation. So what we're talking about is a wind turbine, right? These blades sweep out some area that has a radius of this circle that they sweep out has a radius of r. Air moving across that, if the wind speed is too slow, then we don't care about that because it won't affect our wind blades. If it's too fast, then we'll have to shut down the turbine. So we're really only interested in wind of a particular speed in order to calculate the power potential that's available, right? So let's draw a cylinder and then talk about the air within that cylinder. So there's air inside this cylinder, and if it starts here at a specific time and travels across this distance L, then that's the air that we're interested in. Now, of course, this also has the same radius r, which gives us some area, right? And so now we can talk about the contents of this cylinder. What's in this cylinder? Well, some air molecules. The air that's in this cylinder has some density. Density is given by the equation, and again, there's that rho. Let me try that again. Rho. Any density is given by the amount of something, the mass of a thing, divided by the volume of the thing, right? So density is a mass per unit volume. If we look at the volume of this cylinder, we recognize that the volume is given by the area times the length. So we can plug that in, replace the volume for what the volume represents, and say that the mass is given by the area times the length. What I want to do is rework this so that I have mass by itself. That's no problem. We can just say mass equals the density times the area times the length. That's not too bad, right? So, but again, what we're talking about are air molecules in motion. So since they're moving, probably best to use an equation for kinetic energy if we want to know how much energy is in this cylinder. So what's the equation for kinetic energy? Well, E sub k, kinetic energy, is equal to 1/2 times the mass times the velocity of the object that's in motion. Well, all right, okay, so what do we do? We don't really want the energy, we want the power that's available from the air moving across these blades, right? And we know that power is equal to the amount of energy that's available to us in some amount of time. So we can say that power is energy divided by time. And so let's plug in our energy term, 1/2 mv squared divided by time. Now I want to go back to this term that we used right here. Again, it's the kinetic energy is 1/2 times the mass of the object that's in motion times the square of the velocity of the object. So this mass I want to replace with what this mass equals. We're talking about the mass of the air that's inside the cylinder. So the mass of the air is equal to the density of the air times the dimensions of the cylinder. So we can replace this mass with what it equals and say that the power is equal to 1/2 times the density times the area times the length times the square of the velocity divided by time. So this right here is the mass that we just plugged in to right here. Pretty straightforward, right? Well, if I look at this, I recognize that a length per unit time, a mile per hour, a meter per second, the length per unit time, well, that's also a velocity. So I can rewrite that as 1/2 the density times the area times the length divided by time, which is a velocity, times this other velocity, which allows me to say that the power is equal to 1/2 times the density times the area times the cube of the velocity. We're almost there. I'm going to move this area over because this is the power that's available in that area. So if we're going to talk about power per unit area, let's make that ratio. Power divided by area is equal to 1/2 times the density times the cube of the velocity. So the question we have to ask, for a given area, if we let the area stay the same, if we increase the velocity a little bit, what happens to the power? Does it also go up a little bit? Does it stay the same, or does it go up a lot? Consider that we're talking about the cube of the velocity. So as the velocity increases by, say, 2 miles an hour, what happens to the power that's available for that same area? Think about that and let me know.